viewers, in today's class we are going to discuss yet another important and very conceptual problem from integration, right? So in this class we'll solve this important integral which is from minus infinity to infinity, and the integrand is 1 over x square plus a square whole square, right? So viewers, here in this lecture we'll solve this integral very easily by the method of substitution and by applying the properties of beta gamma functions, right? So viewers, this integral can also be solved by the method of Cauchy's residue formula, right? But here we'll restrict ourselves to the application of beta and gamma functions, and we'll take up the calculus of residues and the contour integration in our next videos, right? So let us solve this integral. So let us take this integral as I, right? And here I will make the substitution that is x square is equal to a square t, right? So t is our new variable, right? So x can be written as a square t raised to the exponent 1 over 2. So x is a times square root of t, right? Okay, now let us differentiate x with respect to t. So we have dx over dt is equal to a being constant. So the derivative of square root of t is given by 1 over 2 times square root of t, right? So now we can write dx as a over 2 and t raised to minus half, and here we have dt, right? Okay, now see here the limits of integration are from minus infinity to infinity, right? So here we can simplify this integral by using a property of definite integrals, that is we can write I is equal to 2 times 0 to infinity dx over x square plus a square whole square. So here we have applied an important property of definite integrals, which says that minus a to a f of x dx is equal to 2 times 0 to a f of x dx, right? Provided this function or this integrand f of x is an even function, right? So here f of x is given by 1 over x square plus a square whole square, and we can easily see that if we replace x by minus x, then f of minus x is equal to 1 over minus x square plus a square, and here we have square. So this is 1 over minus x square is simply x square, and this is a square whole square, right? So we again get the function itself, right? So f of minus x is equal to f of x, which suggests that the integrand 1 over x square plus a square whole square is an even function. So we can apply this property. So minus a to a, here we have minus infinity to infinity. So this is 2 times 0 to a, 0 to infinity, and this function f of x, right? So now let us express this integral I in terms of the variable t, right? So we have 2 here, 0 to infinity. Now see here the limits of integration are from 0 to infinity, because when x is 0, then the value of t can be calculated from this expression. So the value of t is also 0, and when x is infinity, that is when x tends to infinity, then t also tends to infinity, right? So we have 0 to infinity. Dx can be replaced by a by 2, t raised to minus half. Here we have dt, and in the denominator we have x square. X square can be replaced by a square t plus a square, and here we have square, right? So now this 2 and this 2 get cancelled, and we can take a outside the integral. So we have 0 to infinity t raised to minus half dt, and here we can take a square common. So now when we take a square common, we get a raised to 4, right? Because here we have a square, we have whole square. So we have a square t plus 1, and here we have the whole square. So this is 4, and we have here t plus 1 square, right? So here this a and 1a get cancelled, so we are left with 1 over a cube, and we have 0 to infinity, and here we have t raised to minus half dt, and in the denominator we have t plus 1 whole square, right? So now let us rewrite this integral in terms of beta function, right? So we have I is equal to 1 over a cube, 0 to infinity. Here we have t raised to minus half, and t raised to minus half can be written as half minus 1, because half minus 1 is minus half, and t plus 1 square can be written as half plus, here we can write 3 by 2, right? And here we have dt, because half plus 3 by 2 is 2, right? 3 plus 1 is 4, 4 divided by 2 is 2. So we have expressed this integral like this, because we know that beta m comma n is given by this integral, that is 0 to infinity x raised to m minus 1 divided by x plus 1 raised to m plus n, and here we have dx, right? So if we compare this integral with this one, then the value of m is half, m is half, and here this is m, this is also m, and n is 3 by 2, right? So now this integral I can be written as 1 over a cube, and we have here beta of mn, and m is half, n is 3 by 2, so we have 1 over a cube beta of half comma 3 by 2, right? So now we have to calculate the value of beta half comma 3 by 2. So now for calculating this expression, we have another important relation, that is beta mn is given by gamma of m, gamma of n divided by gamma of m plus n, right? So beta half 3 by 2 is given by gamma of half, gamma of 3 by 2 divided by gamma of half plus 3 by 2, right? So now see, we have one important relation in gamma function, which says that gamma of n plus 1 is equal to n times gamma of n, right? So gamma of 3 by 2 can be written as gamma of half plus 1. So this is half, because n is half, so we have half times gamma of half, right? And gamma of half is square root of pi, right? Because we have gamma of half is equal to square root of pi. So here we have now 1 over a cube, and the value of this expression is gamma half. Gamma half is square root of pi, and gamma 3 by 2 is half square root of pi, and in the denominator we have gamma of 3 plus 1 4 over 2, that is gamma of 2. So now the value of gamma of 2 is 1, right? Because we know that gamma of n plus 1 is equal to n factorial, right? So gamma of 2 can be written as 1 plus 1, so that is 1 factorial, and 1 factorial is equal to 1, right? So now we have 1 over a cube, and this is half times the square root of pi times the square root of pi, so this is pi over 2, and gamma of 2 is 1, right? So the value of this integral can now be written as pi divided by 2a cube, right? So here's the value of this integral is pi over 2 times a cube. Hello viewers, in today's class we are going to discuss yet another important and very conceptual problem from integrals, right? So in this lecture we'll solve this integral that is minus infinity to infinity, and the integrand is x square divided by x raised to 6 plus 1, right? So we'll solve this integral by making use of the properties of beta and gamma functions, right? So viewers, we can also solve this integral by contour integration, but we'll take up that topic very shortly, right? So let us solve this integral by first using the method of substitution, and then by applying the properties of beta and gamma functions, right? So let us take this integral as I, right? Now here what we will do, see here the limits of integration are from minus infinity to infinity, right? And the integrand is x square over x raised to 6 plus 1. So we can write this integral as 2 times 0 to infinity, and we have x square divided by x raised to 6 plus 1 dx, right? Because here we have applied an important property of definite integrals, which says that if we have an integral that is from minus a to a f of x dx, then this can be written as 2 times the integral from 0 to a f of x dx, provided fx is an even function, right? So here we can see that fx is x square divided by x raised to 6 plus 1. So if we replace x by minus x, then we have f of minus x is equal to minus x square divided by minus x raised to 6 plus 1. So minus x square is simply x square, minus x raised to 6 is x raised to 6, because here we have even powers, and this is equal to f of x, right? So we see that f of minus x is equal to f of x, so fx is an even function, right? So this integral I can be written as 2 times 0 to infinity x square over x raised to 6 plus 1 dx. So now let us make use of the method of substitution, right? So here what we will do, we'll take t is equal to x raised to 6, right? So that x is equal to t raised to 1 over 6, and here the limits of integration vary from 0 to infinity. So when x is 0, then t is 0, and when x is infinity, that is when x tends to infinity, then obviously t also tends to infinity, right? So here x is equal to t raised to 1 by 6. Let us differentiate x with respect to t. So dx over dt is the derivative of t raised to 1 by 6. So we have 1 over 6 t raised to 1 by 6 minus 1. So this is 1 over 6 t raised to minus 5 by 6, right? So here we have used this result, that is the derivative of x raised to n is nx n minus 1, right? So now dx can be written as 1 over 6 t raised to minus 5 by 6, and here we have dt, right? So now I can be written as 2 times, we have 0 to infinity, t varies from 0 to infinity, x square can be written as t raised to 2 by 6, and here we have in the denominator we have t plus 1, and dx is 1 by 6, t raised to minus 5 by 6, and here we have dt, right? So now let us rearrange the terms. So here we have 1 over 6. So we can now write 2 over 6, taking 1 over 6 outside the integral. We have 0 to infinity. And here we have t raised to 2 by 6. And here t raised to minus 5 by 6. So here we have minus 5 by 6. And in the denominator we have simply t plus 1, and here we have dt. So this is 1 over 3, this is 2 3s are 6, and we have 0 to infinity, and this is t raised to 2 minus 5 is minus 3, and here we have 6, so this is minus half, right? So here we have t raised to minus half divided by t plus 1 and dt, right? So now to solve this integral, we can rewrite this integral I as 1 over 3. We have 0 to infinity, and t raised to minus half can be written as half minus 1, and t plus 1, right? So here we can write 1 plus t raised to 1, right? Here the exponent is 1, and 1 can be written as half plus half, right? So that half plus half becomes 1, and t raised to minus 1 over 2 can be written as half minus 1, right? So why we have expressed this integral like this, because we know the rule for that is gamma function, that is beta mn, is given by this integral, that is 0 to infinity x raised to m minus 1 divided by 1 plus x raised to m plus n, right? So here this integral is now similar to this one, except the variable, because the variable is a dummy variable and it is not going to make any difference, right? So now if we compare this integral with this one, then this is the value of m is half, and n is equal to half, right? So here both the values of m and n are equal to half and half. So now this integral I becomes 1 by 3 times beta mn. M is half, n is half, so we have beta half and beta half comma half, right? So now we know a relation between beta function and gamma function. So beta mn is given by gamma of m, gamma of n divided by gamma of m plus n, right? So beta half comma half is equal to gamma of half. Here we have gamma of half divided by gamma of half plus half, right? And we know that the value of gamma half is equal to square root of pi. So here we have square root of pi, here also we have square root of pi divided by gamma of 1. Half plus half is 1, and the value of gamma 1 is equal to 1. So root pi times root pi is equal to pi, and gamma 1 is equal to 1. So this is equal to pi, right? So the value of beta half comma half is pi. So here we have 1 over 3 times pi, right? So the value of beta half comma half is pi. So now the value of I is given as pi by 3, right? So viewers, this is how by making use of the concept of beta and gamma function, we can solve these kind of integrals easily, right? And moreover, here we can also solve these integrals by the method of contour integration using the concept of residues and the Cauchy's residue formula, right? So we'll consider this topic very shortly. Hello viewers, in today's class we are going to discuss another problem from integrals, right? And in this lecture we'll solve a very nice integral in which we are going to use the concept of beta and gamma functions, right? So viewers, this integral can also be solved by the method of residues, right? Or by contour integration. But here we'll make use of the concept of beta and gamma functions. So let us take this integral as I, right? Now see here what we will do, we'll first write this integral as 2 times 0 to infinity 1 over x square plus 1 cube, right? So here we have used an important property of definite integrals, that is minus a to a f of x dx is equal to 2 times 0 to a f of x dx, provided f of x is an even function, right? So whenever f of x is an even function, then minus a to a f of x dx can be written as 2 times the integral 0 to a f of x dx, right? So f of x is an even function. It implies that f of minus x is equal to f of x, right? So here our integral is from minus infinity to infinity 1 over x square plus 1 whole cube, and f of x is 1 over x square plus 1 whole cube, right? So when we replace x by minus x, then f of minus x is equal to 1 over x square plus 1 whole cube, because here minus x square remains the same as x square, right? So f of minus x is equal to f of x. So we can write this integral as 2 times 0 to infinity 1 over x square plus 1 whole cube. So now let us apply the method of substitution, right? So here I will make this substitution, that is x square is equal to t, right? So we'll take x square is equal to t, or in other words we can say x is equal to square root of t, right? Now see, x varies from 0 to infinity. So when x is 0, then the value of t can be obtained from this relation. So we have t is equal to 0, and when x tends to infinity, then t also tends to infinity, right? Now x is equal to square root of t, so differentiating x with respect to t, we have dx over dt. The derivative of square root of t is 1 over 2 times square root of t, right? So now dx can be written as dt divided by 2 square root of t. So now this integral I can be written as 2 times 0 to infinity, and dx can be replaced by dt over 2 square root of t, and in the denominator we have x square plus 1 whole cube. X square is t, so we have t plus 1 cube, right? So here this 2 and this 2 get cancelled, so we have 0 to infinity, and here we have dt over square root of t, and here we have t plus 1 whole cube, right? So let us write this integral as t raised to minus half dt, and here we have t plus 1 cube, right? So now let us express or rewrite this integral as 0 to infinity t raised to minus half, right? So we can write minus half as half minus 1, right? And t plus 1 cube can be written as half plus, here we can write 5 over 2, right? So what we have done here, we have expressed this 3 as half plus 5 by 2, because 5 plus 1 is 6, 6 over 2 is 3, right? And minus half as half minus 1, right? So why we have expressed this integral like this? Because here we'll use the concept of beta function. So viewers, the beta function is defined as beta of mn is equal to the integral 0 to infinity x raised to m minus 1 divided by 1 plus x raised to m plus n, and here we have dx, right? So now if we compare this integral with this one, then here the variable is x and here the variable is t, and the variable is not going to make any difference because it is a dummy variable. So here we have m minus 1 and here we have half minus 1, right? So the value of m is half, and here we have 1 plus x raised to m plus n. Here we have 1 plus t, because t plus 1 can be written as 1 plus t, and this is half plus 5 by 2, right? So the value of n is equal to 5 by 2, right? So now this integral I is equal to beta of mn. M is half and n is 5 by 2, so this is half comma 5 by 2, right? Now we know an important relation between beta function and gamma function. So beta of m comma n is gamma of m, gamma of n divided by gamma of m plus n, right? So here I is now equal to gamma of half, gamma of 5 by 2 divided by gamma of half plus 5 by 2, right? So here we have m plus n. So this is gamma of half, gamma of 5 by 2, and here we have half plus 5 by 2, that is equal to 3. So here we have gamma of 3, right? So now we have to find the value of gamma of half and gamma of 5 by 2, right? Now see, we know that gamma of half is equal to square root of pi, right? And gamma of 5 by 2 can be written as gamma of 3 by 2 plus 1, because 3 by 2 plus 1 is 5 by 2. So this is 3 by 2 gamma of 3 by 2, right? Because we know that gamma of n plus 1 is equal to n times gamma of n, right? So n is 3 by 2. Again, we can split 3 by 2 as half plus 1 and applying this rule again. So we have 3 by 2. Here we have half, gamma of half. So this is 3 by 4 times square root of pi, right? So now taking these values in this expression, we have square root of pi times 3 by 4 root pi, and in the denominator we have gamma of 3. Gamma of 3 is equal to 2 factorial, right? So 2 factorial is 2, so here we have 2, right? So this is 3 pi over 8, right? Because root pi times root pi is pi, and here 2 fours are 8. So the value of this integral is equal to 3 pi over 8.